Today we've got Professor Paul Fennell from Imperial College London talking about novel capture technologies and new developments, perhaps things that won't happen straight away, but things that are certainly, I guess, bidding for research money and perhaps being planned for in the 30s. Paul, please tell us something about next generation novel technology.
Okie dokie. Right, I need to share my screen. Okay, so I'm Paul Fennell. I'm a professor at Imperial College. And what I'm going to talk about is CCS at the moment, and then moving on to CCS for the future. And then if I was to be, with all of these sorts of processes, I'm thinking about what questions I'd ask about them if I was to be in a process of evaluating them, for example. And then I'm going to tell you why CCU is not the future. Right, so I'm sure that somebody has shown this slide to you before. So this is quite an important plot. It shows the minimum work for separating CO2 from another gas. And you can see that it rises very sharply depending on what the mole fraction of CO2 is. And it becomes quite high for a system trying to take CO2 out of the air. And then as you go up in mole fraction of CO2, you have less minimum work required, which turns out to be quite important. Now, I will say that this is the minimum work, so it's, there is extra work on top of this, and the closer you are to thermodynamic perfection, the better, but this gives you an idea of how difficult it is to do particular separations. So, more dilute the gas, the more work required. You have to pay that separation cost. And if you are separating CO2 from, say, a power station exhaust, let's not forget that you are using maybe a quarter, perhaps a bit less, of the electricity output from the power station gas to capture the CO2 at the exhaust. And because of this minimum work here, if you output that gas, if you let the gas go, the CO2 gas, and then capture it from the air, all things being equal, you'd use 3/4 of the electricity. I decided to put in some Latin here because I believe that we're all now supposed to be Latin scholars, given the new announcements from the government. Okay, so I'm sure that you've seen something like this. This is the current situation. This is what any of the new technologies are competing against. It's post-combustion capture with some form of chemical absorption. And the energy input here is from steam that's diverted from the steam cycle. And that's one of your major costs. However, let's not forget that the actual solvent scrubbing system costs money too. A lot of people are looking at reduction of operating expenses via the minimization of thermal energy required to be input to systems. But they should also, you also need to focus on the operating expense, on the CapEx as well. The capital costs a lot of money in these systems, and you need to look at both the operating costs and the capital costs in order to make an improvement in a CCS system. So what's the future of CCS? Well, in a lot of ways, the future of CCS will continue to be some form of solvent scrubbing. Here we have how much energy you need to put in to your process. Here's the thermodynamic minimum for separation. You can see that we're running about 3 times the thermodynamic minimum, but you can see that with time, processes have become even just bog standard, boring old amine scrubbing is getting significantly better at its energy penalty. And in particular, once demonstration, deployment, probably in this case deployment, happens, I would expect that you will get further increases in the further decreases in the heat duty required. So in some ways, the future of CCS will be what we have at the moment, just with better solvents and critically better process integration, better thinking about how we design our system. So if there's a sufficient CO2 price, you're going to be having solvent scrubbing deployed. I mean, no questions. This will be part of the future of CCS. So lots and lots and lots of text. It's a mature separation technology. It's widely deployed at large scale, and there's decades of experience with oil and gas industry. The critical thing is that you can actually get a somebody will give you a certificate that says that how something will work. It's fairly flexible, etc. The problems are that you've got a high capex, you have a very big energy penalty, and you have some costs associated with solvent makeup and degradation. So that's what you would do. That's what we do now. However, there's limits. You have other systems that have lower energy penalties and capex, and I will say here that I'm old enough to have been told when I was a lad at the knee of, well, actually Gibbons at this time, don't bother working on next generation capture. Solvent scrubbing is going to be developed, deployed, and obtain such a first mover advantage that nothing else will beat it. And this was quite some time ago. And one of the key things that I'm going to say here is that there's a need for continuous development of different processes, because once we actually deploy these sorts of things, the solvent scrubbing, etc., people will come to recognize that maybe they don't want to pay quite such a high energy penalty. Maybe they don't want to pay such a high capex. And we need to have processes and systems ready to take over once everybody recognizes that amine scrubbing is it's something that we have to do, but it's a bit meh. So all technologies, when you're actually developing them, will exhibit somewhat of a learning curve. And, down here, this is when your university professor comes up with the idea and says, hey, this is what I think we could do. Wouldn't this be fantastic? Then a few years later, there'll be a pilot plant and people are like, way, this is fantastic. And then at some stage that will go to a demonstration plant and people will be thinking about the fact that the pilot plant, ignored a whole load of actual real world problems. And when it comes to a demonstration scale system, they have to actually start getting solved and costs go up. Anyway, after a while, you produce a commercial scale plant, and then you start to demonstrate, and your cost starts to come down very significantly. Right, we have here a number of different technologies, and where in, I think this was 2018, we assigned them in terms of where they were in terms of demonstration. I think you can see the one that I'm sort of scabbing out here is direct air capture. I don't know how we managed to say that that was at TRL 7. Let's just say that I wasn't the person with the final say on this plot. And in order to go from demonstration to commercial, you need to have a sufficient carbon tax or other measures to actually push towards development. But what I would say here is other measures are nice to help to create a market, but only, in my view, actually requiring people to pay something like the cost of their emissions will actually lead to them clearing up their emissions. So some of the things I'm going to talk about today: membranes. I'm not going to be talking about oxycombustion. I know there's a lot of people who are big fans of the Allen cycle, etc., 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 but I don't know enough about it to really make a careful point. Some more membranes, lots of different types of membranes, and high temperature solid looping cycles here, chemical looping, calcium looping, and then post-combustion, adsorption, etc. And right up here we have commercial amine power plants. Right, so this is what I'm going to talk about. So membranes, you have some form of membrane separating a region where you have a dilute gas which will permeate more readily through a membrane than a different gas. So here we've got nitrogen and CO2, and we have a high partial pressure wants to look at a new material, I'll sort of ask them, you know, have you done any basic Aspen modeling? Have you actually done any basic modeling of what this would look like in practice? You know, can you know, tell me how it will work? And these things are, you know, not that difficult to do, but are frequently not actually done. And another thing that's important is the order of magnitude costings. Right, these are systems that are being scaled up as we speak. There's some very nice processes such as the veloxotherm process, and that has a big rotating disc which the CO2 gets absorbed onto a wedge and then desorbed later, and the heat gets transferred around in a very, very efficient way. So these are being developed at a reasonable, up to a reasonable scale. So some of the research drivers at the moment is improving the efficiency. How they improve the efficiency is that they avoid some of the thermal penalties that you get associated with the use of amine-based scrubbing, because they prevent any evaporation and condensation of large amounts of water. So in a amine scrubbing system, you have a maximum concentration of the amines that you can use, and by adding in water, you prevent that concentration going too high, and you reduce corrosion, and et cetera, et cetera, et cetera. But one of the issues with an amine scrubbing system is that you could just think about it in some ways as a great big system for evaporating and condensing large amounts of water. So supported material, supported amines get around that. You don't have the water around as well. Lots of work's being done on these, and people are getting the idea now that you need to test them with realistic gases. So, sort of liquid scrubbing as well. Ionic liquids. Ionic liquids are another fantastic chemical process, or fantastic class of chemicals, which are defined as sort of ionic species that are liquids below 100 degrees C. And chemists absolutely love playing around with them. They're cool in terms of the chemistry. And they can pull in CO2 and release CO2. They're thermally stable up to, well, it depends on which ones you're actually using, but you can get ionic liquids that are thermally stable up to around 300 degrees C, which means that you don't have to cool your flue gas before sticking it in. They're good with SO2, so that's marvelous. What's the problem? Well, a number of them are commercially available but haven't been optimized for CO2 solubility. People are looking into that at the moment. The big issue is that a lot of them are basically like treacle. So you have a problem with viscosity, and in order to get an efficient mass transfer in a scrubbing tower, you need something that is not very highly viscous. And so if you need to dilute them to reduce the viscosity, you'll lose many of the benefits of the ionic liquids. So a lot of the time these are described as infinitely tailorable materials. You can choose any anion, any cation you want within these ionic liquids, and tune their abilities very precisely. But unfortunately, in terms of the viscosity, you're tuning the viscosity from awful to really, really awful. So that's a bit of an issue. You also need to look at the amount of CO2 taken up per unit mass, not per mole. Some of these things are great big molecules, and you can take up CO2 onto them, and people say, oh, this takes up 1 molecule of CO2 per molecule, and isn't that fantastic? And then you actually look at the actual molecule and you find that it's a huge, great thing. And in fact, it takes up a very small amount of CO2 per kilogram, which is the sort of important thing when you're pumping stuff around. There's some absorbance that and demonstrations, etc. That's the important thing there. Questions that I like to ask are, what toxic elements are in this? You really don't want your new materials to be adding on very, very highly toxic materials onto your power station site, because the health and safety manager won't like it and won't let them on. It's a really important question for any new material, right? So I had a bit of a look of a review article on MOFs, and I found that, some people are advocating for, oh, here's a fantastic MOF that we might make and we might use for CO2 capture. When you actually look into the structure, it contains cadmium. It's based on cadmium, and that's not going to be a good idea. You've got to have stuff that's not toxic, because bits of it will escape. And lots of, if you have a bit of carbon black or whatever escaping into the atmosphere, okay, that's not great. But you're not going to, poison all the fishies and kill all of the local workers. If you have release of a large amount of cadmium, not a good idea. And you also have to think about what you're actually doing when you're producing these materials. So lots and lots of fun chemistry, lots of multiple synthesis steps, but you have to think about, any byproducts. You have to do life cycle analysis, all that sort of stuff. And same thing, if somebody wants to trial something, well, have they done it at a small scale with bottled gases? Have they done an experiment at a lab scale before they're looking at doing it on a large scale? Other things that are quite interesting is people will give a benchmark for MEA, for example, and will say, we aim to improve by a factor of 2 from the benchmark. And invariably, the benchmark that they'll give you is this benchmark back in the year 2000. And whereas what they should be doing is giving you this benchmark, which, an improvement of factor of 2 from this benchmark is this benchmark. So worth just thinking about things. Right, so on to what I actually work on, which is high temperature solid looping cycles. Now, I've told you earlier that you need to pay the piper, and I've told you that you need to pay the enthalpy of demixing, but via a combination of black magic wizardry and thermodynamics, the energy penalty for demixing for these things is paid without you actually knowing where it's paid. Well, I know where it's paid, but it's paid by the drop in exergy of the fuel when it goes from a very high temperature to a slightly less high temperature, but we won't go into that. Right. So the advantages of these are just too many to list, and the disadvantages are, you know, none at all. And did I mention that I've written a book on these? Okay, maybe we should go into a little bit more detail on this, because they do have some disadvantages. So calcium looping is something that I spent a few years working on. Again, it's a reversible reaction between calcium oxide and CO2 to form calcium carbonate. You take your CO2 out from your flue gas here, and you take it into a calciner here. You burn some coal with some oxygen, and you produce a pure stream of CO2 coming out here. So again, all it's doing is capturing the CO2, concentrating it up, and then releasing it here. The regenerated calcium oxide then goes back to the carbonator, and you cycle around and cycle around and cycle around, producing pure CO2 from your flue gas. It's the advantage of the limestone's cheap and non-toxic. It's based on mature circulating fluidized bed technology. It has a low energy penalty, and you can, in certain configurations, turn this to a zero energy penalty, although that requires some mucking around with heat pipes and things, which probably won't actually be done, because this air separation unit to produce oxygen, it's fine. It doesn't produce that much, doesn't require that much energy. And great synergy with cement, I think I mentioned last time I was talking, and there's no sulfur removal required, because the limestone will pick up the sulfur as well, and you get a 2 for a 1. It does eventually poison the material that's flowing around, but who cares? It's limestone. You can just chuck it out into a cement works and make cement with it. Anyway, so that's that system demonstrated again. And the key thing here is that the heat that you put in your calciner, the heat that you put in here, because the temperature of the carbonator is around 650 degrees C, you can take that heat out into a nice efficient steam cycle, and that is why the energy penalty for this system is low. It's because essentially you put in energy here, but you can take it back out again to form electricity here. So everything's nice and efficient. Been demonstrated up to a megawatt scale now, nearly 10 years ago. Was likely to be being taken on to large scale, but then the financial crisis happened and nobody had any money, so people were more interested in not going bankrupt. Chemical looping, similar process, except instead of looping CO2 round a system, you're actually taking oxygen from the atmosphere and feeding it to your fuel. And because the oxygen from the atmosphere never actually mixes with, or doesn't mix with nitrogen in your combustion system, you end up burning, so essentially you burn a fuel with a metal oxide, you produce CO2 and water, and then you produce the metal around, and metal cycles around, taking oxygen from here to here, and that's how chemical looping works. Bit more technically challenging than calcium looping. Got stuff going on at high temperature, so a bit of a challenge, but not not a huge challenge. I won't go into this. I'll say that this has been being looked at for quite some time, and Darmstadt has a demonstrator. Essentially, this is up to about 1 megawatt as well, and there's lots of desire to get this up to the sort of 10 megawatt scale. The Energy Technologies Institute did look quite seriously about building a demonstrator, but they decided in the end that they weren't going to, and went down the tidal energy systems, I think, in the end. Right. Questions to ask, what's the material? Has it been tested with realistic gases at realistic scale? And again, process modeling, etc. How is this an advance over the state of the art? Right. So I've gone through on a whistle-stop tour some of the basic CCS technologies. Essentially, membranes, great. They have some, I've seen some very, very low costs of capture potentially associated with them, but they might be susceptible to damage and to materials in the flue gas. Adsorbents, again, being demonstrated, some very large, some actual large-scale demonstrations gone on with those. Nice technology. I have to be careful about what is actually in the adsorbent. And calcium looping, chemical looping, those sorts of things. Demonstrated at the scale of up to a couple of megawatts, needs to be demonstrated at larger scale, and the same caveats apply as everything else. Now, CCU, CO2 utilization. I'm just going to have a very brief chat about this, since everybody says, well, why do we use this CO2? We're not going to use the CO2, right? Absolutely not. And anyone that says that we are doesn't understand either economics or scale of things. Global use of CO2 comes in at up to 227 megatons. We're producing about, sorry, that's the global scale. And, here's the utilization, sorry, the production. That's just for the USA. And the sources outweigh the sinks by several orders of magnitude, by a factor of 150. The storage of CO2 is frequently short term, and that's especially true for the largest sinks, which are methanol and urea. The use of CO2 as a novel feedstock is a good idea if it's justified in the economics, but it will not have a significant climate benefit, particularly if the storage is short term. But also, all of these do not use enough CO2 to make a dent in the total amount of CO2 that we're producing. Right? So, they do not have a significant climate benefit. Some niche markets exist, but if you produce sufficient material to have a significant climate impact, you'll flood the market and crash the price. CCU is inherently non-scalable. And there's some more stuff that demonstrates again why CCU is inherently non-scalable. We use 0.6% of global CO2 produced. It's not realistic to consider CCU as an alternative to CCS. I will say that I consider carbonation of waste materials produced building products as a good idea. That is because it is solving a different problem. It is producing a useful material from a waste. It is a waste treatment process. CO2 is very stable. it reacts with, it doesn't react with many other compounds, and it's why it persists in the atmosphere for a long time. Conversion of CO2 to high-value products is challenging and requires input of energy, and you need to rationally carbon account for that. And, you know, short-term storage of CO2, not a good idea, right? And long-term storage needs to be, would have to be in very large quantities. So, you know, you're not going to be producing enough of any of these materials to significantly affect climate change. So the decision is not to choose between CCS and CCU, but which CCU options best complement CCS. You will not make a scalable process with CCU. So in conclusion, CCS technologies are well understood and are considered mature. There's some, you know, solvent scrubbing. Go pick it off the table, put it on your process, and, you know, absolutely fine. There will be some improvements, but even with the current technology, we could just deploy it today. Right? Deploy amine scrubbing. It won't be very efficient. There are more elegant systems, such as the ones that I work on, but absolutely deploy it today. But, you know, keep on developing future technologies. Otherwise, we'll just get stuck with the relatively poor current technology. The choice between CCS and CCU is a false dichotomy. There is just not enough market for any CCU process, and anyone that says that there is selling snake oil. CCU options are only valuable to support CCS deployment targets associated with meeting our climate targets. And there's some references. Right. We all clear on CCU. Thank you.